Great. So digital currencies have gotten a lot of attention lately. You'll hear about another one later in the session. But what we're going to talk about today is how to make them interoperable. This is a crucial problem for making them actually useful in practice. We don't want to force everyone around the world to use a single platform. And more importantly, we want payments to be interoperable. A sender should be able to send money to a receiver, and the sender might have one currency, and the receiver might want a different currency, and that transfer should happen seamlessly and at a fair exchange rate. So what this means is that we need efficient infrastructure to trade one digital currency for another. And this infrastructure has to be fast, it has to charge near zero fees, and it should give everyone a fair exchange rate. Now, this is shared infrastructure, so it should be jointly operated by stakeholders around the world, and not centrally controlled by one government or bank. Now, the trendy way to do this would be to build an exchange inside of a replicated state machine, throw it on top of a decentralized consensus layer, and call it a blockchain. But is blockchain actually a really good way to build an asset exchange? Well, if you look at current systems, the answer is no. Current systems do maybe dozens to a few hundred transactions per second. That's this line on the bottom here. And we need something that's way faster than that. Now, state of the art for scalable replicated state machines does substantially better in this context, but it's still not nearly as scalable as we would like. So today, I'm going to present to you SpeedEX, which is a replicated state machine that gets linear scalability. Now, this graph here is just for payment transactions. So great, we can do linearly scalable payment transactions. But we want to build an exchange. That's a much harder problem than just doing payments, because we don't need just computational performance. We need good economic performance. The exchange should be as liquid as possible, and it should give everyone a fair level of access, and it should give everyone a fair exchange rate. So how does this work? Well, if you've ever traded on an exchange, you've seen a graph like this. This is an order book. Typically, the exchange will maintain a list of offers to buy and sell an asset. And when I send an offer to the exchange, either it gets added to the books, or it gets matched with and consumes an offer already on the books. This means that every order modifies the order book, and every trade can happen at a slightly different price. This is the root of all of our problems. Why? On the computational side, every transaction is a read, modify, update operation on a small set of shared data structures. This is the worst case for things like optimistic concurrency control and traditional software scaling techniques. On the economic side, this leads to a lot of front running, often seen as like what's called high-frequency trading. A well-connected network participant can insert transactions between user transactions and siphon off liquidity from the network and add computational load to the exchange. In a currency context, we also have what we'll call cyclic arbitrage, which is that if I'm trading from one, say, one non-USD currency to another non-USD currency, I might be able to trade directly, but I'll probably get a much better exchange rate by taking my currency, selling it to get USD, and then selling that USD to get the receiver's currency. And I might get a good exchange rate like this, going through USD. But I might also get a good exchange rate going through euro, or through pounds, or through yen, or some other intermediate currency. And every time that I take a suboptimal choice, in particular the optimal choice is always a combination of paths, every time I take a suboptimal choice, I'm leaving money on the table. That means that other people will come and compete to extract that money that's left on the table by sending payment around cycles. And these competition for cyclic payments adds significant computational stress to the exchange, and has caused serious problems for exchanges in practice, for decentralized exchanges in practice. Now, we don't have a graph that looks like this. We actually have, in practice today, maybe 5 or 6 different USD peg tokens, and so the graph is much more complicated. User experience is terrible, and the market overall is not as efficient and liquid as it should be. So I'm going to present to you today SpeedEX, which is a design for an exchange based on trading in batches. Instead of processing trades one by one, SpeedEX is going to take as input whole blocks of offers and process them all at once. So I want you to throw away your intuitions about how order matching works in a traditional context. We're going to do it a little bit differently. So what are we going to do? Right, so first, SpeedEX takes in a batch of offers to trade. And then it looks at the entire list of all the offers that it has. And it sits there and it thinks for a while. And after a while, it comes up and with a valuation for every asset. So for example, maybe it decides that the value of $1 is 9 units, and the value of a euro is 10 units. These valuations imply exchange rates between every asset, right? So say 9 euros here would trade for 10 USD. So then it takes these exchange rates, and it goes to every offer on its books, and it checks, is the exchange rate greater than the offer's minimum limit price? And if it is, the offer trades, and if it doesn't, the offer doesn't trade. Now, this is where we're differing from traditional exchange semantics. We're not matching offers to buy and sell. The counterparty for all these trades is the SpeedEX engine. In particular, SpeedEX is taking is making the trade for all these offers, and as I've cooked up the example here, none of these offers could be pairwise matched. So you should ask, where do these valuations come from? And well, we'll say that first of all, the set of valuations is clearing if after this whole process, SpeedEX has no surplus or debt. And so I've cooked up these valuations to be clearing, and as you can see, the engine takes in 10 USD, and it puts out 10 USD. It takes in 9 euros, and it puts out 9 euros, and so on and so forth. Now, it turns out that for any set of offers, there always exists a unique set of valuations, unique up to rescaling, that clears the market. So our core technical task here is to figure out how SpeedEX can surface these valuations. I'm going to point out, because they're unique, SpeedEX doesn't have to make like a strategic decision about how to engage in this market making. Great. So why should we do this? Right? Well, suppose that we can compute valuations quickly. Then everything else in the exchange commutes. That means that we can essentially get linear scalability for the rest of the exchange. And in fact, we can implement almost the entirety of the system with just hardware-level atomics. On the economic side, because everyone trades at the same set of exchange rates, there's no front running within the batch. I can buy and sell something in one batch, but I'll just get the same exchange rate, and everything cancels out. This also means that users don't need to hyper-optimize their limit prices, and they don't need to hyper-invest in ultra-low latency network connections. They'll just get the same price as everybody else, and we treat everyone fairly. We also eliminate the cyclic arbitrage problem. If I send payments along a cycle, everything just cancels out, and I don't need to worry about specifying a set of intermediate assets or paths. Now, this is not the first. We're not the first people to propose executing trading in batches. This has been discussed in the traditional economics literature as a response to high-frequency trading. New York Stock Exchange also uses batch auctions for opening and closing the trading day. But these batch auctions trade between 2 assets. And when there's 2 assets, it's very easy to compute the market clearing prices. But when there's many assets, all traded in one batch, nobody thus far has been able to crack the price computation problem. So that's what I'm going to tell you about today. What I'm going to do today is show you how to compute these market clearing valuations efficiently and at scale. Once we have this algorithm, then we can feasibly instantiate this novel market primitive of scalable batch trading. And once we can do that, I can use that to build a high-performance system design around it. So what do I mean by computing clearing prices? Well, in the 2-asset case, it's easy. Right? I have a supply curve, and I have a demand curve, and I'm trying to find the point where these curves intersect. So the 2-asset case, I can do this by binary search. In the many-asset case, well, now we're optimizing over a high-dimensional simplex, and we're trying to find the intersection point, not of 2 curves, but of many higher-dimensional curves. But the idea is the same. We're trying to find the intersection point of a bunch of different curves. It turns out that this reduces to what's called the problem of computing equilibria in Arrow-Debreu exchange markets, linear markets. And so this problem has been studied in the theoretical literature. But if you try and apply any algorithms from the literature out of the box, you'll run into 2 problems. The first is that they're all really slow. And I don't mean that implementation-wise, I mean asymptotically. In particular, everything has runtime that's polynomial in the number of open offers on the exchange. And if even a small fraction of the people around the world use an exchange like this, the number of offers might be in the millions or tens of millions, or just extremely large. And so anything polynomial in something that big is just not feasible. Again, we have to run this algorithm every block, so we need the algorithm to run in like less than a second, say. So what we're going to do is we're going to pick an iterative algorithm from the literature and then make it fast. Basically, the algorithm you pick, is that you pick a set of candidate prices. You compute these supply-demand curves at a particular set of prices, and then you adjust based on your basic Econ 101 intuition. If supply exceeds demand, you lower the price, and so on and so forth. Now, the runtime of this algorithm at each iteration is dominated by the act of computing these supply and demand curves. And for that, we can take advantage of market structure that we have here that's not present in the theoretical literature. In particular, every offer to trade is from one asset to one other asset. So we can group assets by trading pair, sort them by limit price, and then just do a bunch of binary searches to efficiently compute these supply and demand curves. This gets the runtime down to essentially logarithmic in the number of open offers. We also need to sort the offers, but you can do that incrementally batch by batch, and so that becomes not a huge runtime consideration. Concretely, if you're careful about the cache performance, you can get the runtime per iteration down to about 100 microseconds, even when there's like millions or tens of millions of offers to deal with. And we need about 1,000 or 2,000 iterations in order to get good prices. The second problem you'll run into is that all of these algorithms are approximate. In fact, even writing down an exact set of solutions might require like an arbitrarily large number of bits. And so we need something that's efficient. And that means we need to approximate. But if we just apply these approximate algorithms out of the box, they will do all sorts of nasty things. Particularly, they might mint money. They might make trades that people didn't ask for. And they might just steal money from users. Right? So we can't do that. We're working with real money. So we need to be careful about what kinds of approximations our algorithms do. So the first thing we're going to do is we're going to smooth the limit price thresholds. Right? There's an edge case here, which is that even at exact prices, if your limit price is exactly equal to the market price, then maybe your offer trades, maybe it doesn't, or maybe it partially trades. This is how things work in a traditional exchange as well. So what we're going to do is smooth this out and say that if your limit price is very close to the market price, but just a little bit lower, then maybe your offer will trade fully or partially or not at all, but only in this tiny little range next to the market price. In practice, we're going to use a threshold of about 2 to the minus 10 or 0.1%. For an iterative algorithm, this reduces the amount that an algorithm iterates and oscillates around these sharp thresholds. We're also going to allow the exchange to, like every exchange, charge a small fixed fee. This essentially relaxes the notion of market clearing to allow SpeedEX to take on a surplus but not debt. Experimentally, again, this fee is for computational efficiency rather than profit, so we're going to drive it as low as we can. And in practice, we're going to use about 2 to the minus 15, or a fraction of a basis point. What this does is that it expands the region that we're trying to look for. Right? Instead of a single point, we're looking for a reasonably tractable neighborhood of that point. So we get a range of possible clearing prices that we can accept. Now, once we have this prices, we need to turn that into a set of trades. And we can do this by solving this linear program here. Don't look at it too closely, but it's efficient to solve because we can take advantage of the same market structure decomposition and make it the size of it only depends on the number of assets. In practice, what it's doing is it's maximizing trade volume subject to these approximation constraints. Right? And so this just guarantees that any approximations that we have take these forms of a fee or offer smoothing. Putting this all together, we ran SpeedEX on a set of 48-core systems. And I want to point out 2 things. The first is that we get near linear scalability. If you go from 6 threads to 12, you about double throughput. 12 to 24, you about double. And then 24 to 48, you don't double, but you get about 1.5. And that's because SpeedEX starts contending with a lot of background threads that are also working here. But up until that point, we get near linear scalability. And what the scalability does is, well, it's nice to say that, hey, we can get 200,000 trades per second. But what's really important here is that while we implement a set of basic features that we think any exchange would want, but any real system is going to have more features, more users, more bells and whistles, more XYZ. And everything slows every transaction down. And so what the scalability does is lets you compensate for that. Instead of having a trade-off between extra feature or reasonable throughput, you can maintain constant throughput and compensate for adding features by adding more CPU cores to your system. I also want to point out the x-axis here is the number of offers that are open on the exchange, and our throughput only very slightly declines as the number of offers increases. This is due to the logarithmic dependence, essentially. So we actually have two implementations of this. One is the self-contained implementation that I've benchmarked here. This is about 30,000 lines of code. Now, we also prototype this within the Stellar blockchain, which is one of the older layer 1 blockchains. And this prototype only added about 2,000 lines of code to the Stellar system. So what's going on here is that this prototype only implements the commutative semantics, the scalability, and the price computation, not all of the parallel performance. And this is great for an implementation because the semantic changes are the only things that have to go through a system-wide coordinated so-called hard fork upgrade. Once you have a nice set of semantics like this, then you can implement the parallelization asynchronously without coordinated upgrades. And this makes deploying such a system much easier. So circling back to our original question, right? Is a blockchain a good way to build an asset exchange? And no, not if you want to build traditional order matching semantics. But in fact, the answer is yes, right? And the answer is yes if you're willing to make the problem harder for yourself and solve more problems at the same time. So what we did here was by changing the semantics a little bit, we got a system that has linear scalability by making trades commute, and simultaneously, we're eliminating a common type of front running and improving market liquidity. All in all, right, to get scalability, what we did was we let go of traditional semantics. And in fact, this is a good thing in a lot of other ways, right? So concretely, what we built is SpeedEX, which is a decentralized exchange that can handle more than 200,000 trades per second on 48 core commodity hardware, even when there's tens of millions of offers open on the exchange. Thank you very much.